Chapter 7 is about ocean circulation, or otherwise known as currents. And usually we sort of just jump right into the notes, but I want you to look at this picture. It looks like sort of a painting, but it's actually a computer-generated image. It's compiling thousands of satellite images. These satellite images go in and measure different currents, and the white lines represent both the water movement and duration. So the longer the line, the longer the current. And also the brighter white the line, the stronger the current. We're centered sort of right over, Florida in this picture. And the bright white line right there is the Gulf Stream. It's one of the strongest currents there are. But you can see there are surface currents all over the surface of the Earth. And this is actually what you would see. And they kind of go in all different directions. But I will post an animation that shows what these look like in sort of real time when they're moving. It's sort of impressive. So why do we care about ocean currents? Or maybe you don't, but you should. And here's some of the reasons why you should. We always start with a basic definition. Currents are the masses of ocean water that flow from one place to another. You probably could have guessed that already. We are going to break ocean currents up into two types, surface and deep. The surface ones are about the top 10% of water. Deep are the bottom 90%, and they have kind of different characteristics. And they're vitally important currents towards understanding climate. Snowed this past week. We will get to a chapter on climate, but climate's sort of a big deal lately. You should care about the climate. The currents themselves transfer 1/3 of the heat from the equator towards us in the temperate regions, and then distributes the last of it to the poles. If the current suddenly stopped moving, our coastal climate, just our entire climate of our planet, would suddenly become much colder. We would actually have glaciers that come all the way down to about South Carolina in the northern hemisphere. So ocean currents are an important concept. They account for the fact that life can live all the way up into Canada easily. We can classify currents based on their own temperature. So we have cold currents that flow towards the equator. These give rise to sort of dry conditions, less humidity in the air. In terms of examples, the Canary Current would be one. The warm currents that flow from the equator towards the poles, like the one off of our coast, the Gulf Stream, provides nice humid conditions and makes the climate a little more temperate. Besides the importance of climate related to currents, they also bring oxygen to the deep ocean floor. Oxygen is not generated much below 1,000 meters because there's no light, so there's no photosynthesis. So the deep currents bring oxygenated, nutrient-rich water down to the life on the bottom of the ocean floor, which is why any life can exist down there. Even at the hydrothermal vents, which utilize other things such as hydrogen sulfides to produce energy, they still need oxygen, and that oxygen still comes from the surface current and is carried down there by deep currents. So currents influence life and the abundance of life and things like that. So one of the things we're going to sort of hammer home is what causes surface currents, and then we're going to talk about deep currents and how they're driven by density. So surface currents are primarily driven by the wind belts, and their motion of the current is mostly parallel to the surface of the water. We'll talk about Ekman spiral in greater detail. Then those surface currents are acted upon by Coriolis force, which we've talked about a little bit in the past. Deep water currents are a little different. Deep water currents are primarily driven by density. That's why it's frequently called density-driven circulation. And in this chapter, we talk about them a little bit like they're completely separate. Surface currents are one thing and deep currents are another. But we saw that super awesome movie, The Day After Tomorrow, and where the surface currents shut down, that can actually cause the deep water currents to shut down. So we're going to talk about that in greater detail as we move on. We're also going to talk about this in a little more detail, but how do we measure surface currents? So there's kind of a lot of information on this slide. There's some direct measures, and that's where we use different types of float meters. And I'll show you pictures in class as we go through and do the lab. But there's float meters which are intentional, where they're called drogues is one type, or they used to use these things called drift bottles, which are what they sound like at the bottle, and they put a note in it, and they ask you if you find it, where did you put it, where did you find it? And they track where they were dropped off and let go. So intentional float meters are one method. Then there's inadvertent. We'll talk about, there's a little blue box in the book, and we'll do a slide about it. These inadvertent measures for measuring surface currents are shoes and duckies, as you can see in this picture. This is 7B right out of the book. Then there's propeller meters, which is if you want to measure current in one specific spot, you go out and it sort of puts a little fan into the water, which spins, and we can tell how fast the current's moving by how fast it is. Float methods are interesting because they tell you currents over long distances. Propeller give you sort of an instant snapshot of what the current is doing right there. There's also satellites. The satellites are becoming more and more common. They are an indirect measure. Topex Poseidon is probably the most famous satellite that's used to measure surface currents. We can also use a Doppler effect. I don't know if you remember Doppler effect from your super fun days in chem and physics, but basically the change in color of something. Let me give you a more classic example. If you ever hear an ambulance coming towards you, the siren has a different pitch than it does when it's moving away from you, and that's because it's sort of the observational effect of the wave is moving towards you while the object making the wave is moving towards you. This happens with when they use color meters to look at water. Water that's moving towards whatever's measuring it has more of what we call a red shift, and water that's moving away is a blue shift. So, and then there's pressure gradients. We're going to talk about that when we talk about geostrophic circulation. This is, hopefully you remember this from chapter 5. This diagram is an example of a depth profile, and it would be, you can sort of use these, we use these to look for water masses before. We can also use them to look for currents. Currents is movement of water masses. So some of the deep currents are measured looking at, depth profiles, but they're also used by, we sort of let devices go in them. Probably the most famous way or best way to measure deep currents is to look at radioactive isotopes. Where did most of this come from? Tritium. It's not just a plot device in Spider-Man. Tritium is a radioactive isotope of hydrogen, and almost all of the tritium on this planet is left over from the hydrogen bomb testing we've done all over the planet, particularly the stuff in New Mexico and along the Bikini Atoll. And those two have different sort of radioactive fingerprints, so they can trace, because they know when those explosions occurred, each explosion has its own little fingerprint. We can trace how long it took for that tritium to get there. Right now going on, there's another huge chemical tracer being dumped into the Pacific Ocean, and that's the radioactive materials from Fukushima. And there are actual scientists out there looking for those tracers now. It'll be another way to measure surface currents, unintentional as it may be. And then temperature and salinity diagrams we talked about before. You can see different water masses just by dropping, say, a CTD through the water. So there have been a bunch of unintentional releases of stuff. So they're usually floating objects. The two most common examples are shoes and these like tub toys. So in 1990, there was a carrier ship coming from Asia, probably to Long Beach, California, and not far off of Hawaii, there was a huge storm, and 61,000+ of the containers, of the shoes were released. Basically, they fell overboard. And these shoes were Air Jordans, which in the 90s were like a really big deal. So when people would find them on the beach, even if it was just one nasty, soggy shoe, they would hold on to it. And people started using the limited internet that there was to start posting, oh, I have a size 9 left shoe, and other people would say, oh, I have a size 9 right shoe, we should trade, or I guess that wouldn't work out, but people would exchange shoes. Scientists went back later on and used these to find where people found them, and they were actually able to trace some of the largest trace of released objects to sort of measure different currents. Not only would they find out where they were found, but when they were found. So this gives the scientists both speed and direction of currents, which is kind of an interesting idea. And 2.6% of these Air Jordans were recovered, as opposed to when they let go of drift bottles, they usually get like 1 to 2%. The most ever was 2.4. And so this was sort of a unique opportunity to study currents. Then in 1992, there were a bunch of plastic tub toys released, which is kind of funny, rubber duckies floating around the ocean. And they were found all throughout all sorts of places. Alaska, then up into the Arctic. They got caught up in the Bering Strait. Eventually ended up in the North Atlantic and later North Europe. There are some people who claim there were some found down in South America. I don't know how true that is. But using these floating objects was a way to really accurately trace currents, direction, and speed long before we had satellites that could do so. Next one, we're going to talk about surface currents.